Hi class, this is the second lab for the week and this is Beer's Law and Spectrophotometry. This is a good lab, however I'm not a fan of it having two labs in 1 week. Not this lab. This lab is longer and it takes a lot of time. So I strongly suggest you do this lab first. Anticipate to spend some time on it, and we haven't covered this chapter yet. So I feel that the information in here can get lost. I wish this had been scheduled later, but again, I don't make the schedule and I don't have a say in it. So let's get started, and I will do my best as much as possible to help you understand this lab. Colored solution. What makes a solution appear a certain color? A solution will appear a certain color if it absorbs the complementary color, which is the opposite color in the wheel. So for instance, let's look over here. If a solution appears red, then this means that its primary absorbing is green. So it's going to absorb green, and red is what you're going to see. Red is what's going to be reflected out. And all these numbers are wavelengths. So you will never see another color at a certain numerical wavelength. These are fingerprints, these are addresses. So you'll never see orange in the 400 range. It's going to be between the 6 and the upper 500 range. Every color has a specific numerical wavelength, and it will always be that numerical wavelength. So down here saying white light containing all the colors shines on the sample, but as you see, green is the one absorbed, but you're going to see this is red. Everything else will just get transmitted through. It's not going to interact because it's not going to be at the wavelength that's going to cause it to interact with the solution. How do we do this? How do we know about these values in the wavelengths? We use a spectrophotometer. A spectrophotometer measures the amount of light absorbed by a sample. So to me, this lab is a little difficult to communicate online, but had we done this in lab, and we probably would have, it's a very simple lab. It's really not a difficult lab at all. But to try to put this online is a lot harder when you're not really physically able to do this in front and you can see what's happening. So we have a light source, and the light source is not the same as the on button. There's two buttons. You have to turn it on and you have to turn on the light source. And these light bulbs are extremely expensive, so you have to make sure when you turn them on and turn them off, everything is wear and tear on these. So I numbered this. 1, a light bulb emits a white light. Light passes through a slit to form a narrow beam. A diffraction grating separates the colors of light based on their wavelengths. Another slit allows just one color to pass, and light passes through the sample, and a detector measures the final amount of light. So you would use certain wavelengths in order to have the one color pass through and so forth. It's not just random. And this is a cuvette. This is what we normally use. And this, of course, is not in a spectrophotometer. It's just sitting on a balance with a laser through it. But that's exactly what would happen. A laser would go through it and light would pass through, and we would have a numerical value for it. So what are we looking for? We're looking for either absorbance or transmittance. Absorbance is capital A, is a measure of how much light is absorbed. That's the one we're interested in. It does not normally have units. So a light's going to pass through. The less light that gets through, the greater the absorbance. So more the light is getting pretty much, in simple words, stuck in here, and less is being traveled through it. If it was not as intense, if the solution is not as intense as it is or is concentrated, then more is going to pass through it. Another measurement that is related to absorbance is percent transmittance. It's exactly what it means, how much light passes through the sample. It is different than absorbance. So if a light passes through water, what will the percentage of transmittance be? It's going to be 100 because it's a clear solution. It's going to pass straight through it. So a color solution is irradiated with white light. Some wavelengths are selectively absorbed. The other will just pass through. So a particular energy of light, which corresponds to a particular wavelength or color, is absorbed and disappears. The other wavelength that is not absorbed and passed right through. When light is not absorbed, it is said that the light is transmitted through the solution. So that's basically light's just passing straight through that cuvette and nothing's happening. And the more light a solution absorbs, the less light is transmitted through the solution, which is exactly what I repeated in the previous one. So if you look at a color wheel, it shows the complementary relationship. So something that's across from it, that's the complementary relationship. And whatever's absorbed, you're going to see the other color. So if orange is absorbed, you're going to see a blue solution. and vice versa. Absorbance spectrum. The absorbance spectrum is a graph of the absorbance of a solution at different wavelengths. An example of absorbance spectrum, there is a peak at 600 nanometers. This uses nanometers. When I think this, I don't know what chapter this is. I think this is chapter 8. You're going to get very familiar with converting nanometers to meters and vice versa, because that's all we use in this one chapter. I think it's 8. Can't remember right now. An example of an absorbance spectrum, there is a peak at 600 meters. What color would you expect this solution to be? So if you remember, I told you there's wavelengths that have certain values. So what are you expecting to see? Well, orange is actually getting absorbed in this wavelength of 590 to 630. So you're going to see a blue solution. Since the solution is absorbing orange, it must appear blue, which is a complementary color. This is absorbance max. When you would be in a lab, you would actually test a bunch of different solutions and you would try to find the absorbance max, the highest number that's going to allow the most absorption in a solution. So wavelength of maximum absorbance. The wavelength of maximum absorbance is called exactly what I said. For best accuracy when measuring the absorbance of several solutions, it is best to measure as close to the max as possible, the wavelength max, lambda max. To find the best solution, the best absorbance max of a solution, you plot absorbance over concentration. So you would plot a number, and this is not it. This shows absorbance over wavelength. This is you determining what that is. But you would get certain amount of values and you would plot them, and it would be absorbance versus concentration, and that would help you determine which is the best absorbance over for different solutions. The wavelength at which absorbance is highest is the wavelength to which the solution is most sensitive to concentration changes. This wavelength is called maximum wavelength, or let's just leave it at maximum wavelength. So again, if you had different solutions, you would plot. That's where this lab is leading. If you haven't read it, where you're going to create graphs. You would plot absorbance versus concentration to determine the maximum absorbance. Okay, so let's understand concentration and absorbance. Which of these two solutions contains a higher concentration of red? So if you understand, concentrated is really dark here, and this one is really pink. So if you can see, A is more darker than B. So a higher concentration leads to a darker color. Which of these two solutions will have a higher absorbance max? Well, if you can see, the higher the concentration, the greater absorbance. So it would be A. You see how the arrow's disappearing and this one's not? What would happen if the wrong wavelength was selected? Nothing. You would have no absorbance. Nothing would be red. So you have to use the correct wavelength. It's pretty much a fail proof. You would go with the knob. There's a knob on this, and I'll show it to you later. And you keep turning it until you see the numbers change, and they will go up and they will go down, and that will allow you to determine which one it is. By the way, if you were to use a solution like this, it wouldn't work. You would get no reading. In fact, it would tell you that it's too high. You would have to dilute this in order to use the spectrophotometer to something that's more like this, or like even these three. If it's too diluted, you will get no reading at all. You'll have to dilute it. All right, so now we're getting into the depth of what our lab is supposed to be for. Beer's law. It is A equals epsilon, B, C. Beer's law is a way to measure the concentration of solutions based on how they absorb light. Data is taken and graphed with a best fit line. So there it is. It's telling you exactly what this lab is about. A is absorbance. There's no units. And how much certain wavelength gets absorbed from the path through the cuvette. Molar absorptivity, or it's also called the extinction coefficient. It's dependent on the substance. It's a measure of how strongly a chemical species or substance is absorbed. A higher value means there's an increase in absorption of light. What this means is that every species that can be used for this for Beer's law and can be put in a spectrophotometer has a molar absorptivity value. And you cannot use the one for the other. So if I have a molar absorptivity value for red, and now I want to put a blue solution, I have to start all over, calibrate, and do the whole thing. You have to consider the fact that, well, for calculations anyways, the molar absorptivity for red is only for red. Molar absorptivity for blue is only for blue. So that's where this is more like a fingerprint for a substance. Path length, it's in centimeters. Width of the tube or cuvette, that's what this is here, holding the solution. It's usually 1 centimeter across, 1 centimeter, 1 centimeter. Affects how many moles that the light will encounter on its journey. The higher the value of B, the light will interact with more moles of solution. And molar concentration, C is concentration, is in molarity. The higher the concentration, there is an increased interaction with the light. All right, so here is a calculation. What is the absorbance of a 0.0054 millimolar red dye sample at 504 nanometers in a 1.0 centimeter cuvette? I think I took this from the video. Pull out all the information you know. So you're given the molar absorptivity, or you'd have to look it up. In this case, you would be given it. You want to know A, you have C, and you have B. So you need to solve this by setting it up. And if you notice, there's a direct relationship. If this is a direct relationship. So if C goes up, absorbance goes up. If B goes up, absorbance goes up. So, and if B goes down, absorbance goes down. If concentration goes down, A goes down. So it's a good kind of idea to look at the formula, and you can see that. So we solve for everything. We have our molar absorptivity, which is the epsilon. We have our path length, and we have our molar concentration. And remember, I told you A has no units, so you should have no units with A. If you did this right, everything will cancel out, and my number is 0.14. Here's a different type of question. The absorbance of the solution at 527 nanometers is 0.49. If the molar absorptivity of yellow dye at 527 is 27,500, over molar centimeters. You know what? I never paid attention to the units to say them. I always see them. What is the concentration of the solution and molarity? So we take the formula again, and we plot it for whatever is being asked for. So concentration is what's being asked for. So we isolate that, plug in all the numbers. And this is a question that is similar to on LabFlow. So I didn't use scientific notation. I keep them all in the zeros, and it took it for that. I also did not use units, even though molarity would be the answer. I didn't. I believe you can use units. I have in the past, but I just got used to not using units, and it's taken it. So I wouldn't worry about the units too much, because if it's a unit that's correct, then it should be marked correct. But again, I didn't use scientific notation on any of this or units. I don't know why. Just didn't. Beer's law, absorbance reading. So imagine you tested the absorbance of 5 solutions, and you can see one is blank with water, and the rest are different dilutions of one solution. So this is what you're going to do. You're going to take these values and you're going to do a plot. And this is where this information will come in. With this data, a graph can be produced to make the data fit a straight line. This is the straight line, y equals mx plus b. What trend do you predict for the relative absorbance readings at max wavelength? So here you have absorbance and you have concentration. So you have enough information that you can plot this. Here is a graph with this data. It's called a calibration graph. It is made using known values, your collected values, and can be used. So if it's a straight line, this is the y equals mx plus b. This is a equals y. And you can see that c is the x. Okay. So to graph this data, what variable would be on the y-axis? The y-axis is always the dependent variable. So this would be absorbance. So the y is going to go here. That's going to be absorbance. The x-axis is the independent variable. This would be concentration. So that's what's going to be down here. All right, so this is something I took, I think, off of LabFlow. If an unknown solution has an absorbance of 0.351, what is its concentration? So how are you supposed to use this? Well, you take the equation from the graph. So you see this is absorbance. I would have written absorbance out, but they did not. And concentration, and there's a title, and here's the equation. The only thing that's missing on here is r squared, and I'll show you what that is in a minute. Okay, so you need to answer this question. How do you do that? Well, you need to know how y equals mx plus b is matching with our Beer's law. And once you know that, this is not a difficult question at all. So what do you care about? Well, based on this equation, you're actually given m and you're given b. You have a in the word problem, and it's asking for concentration with its x. So you're solving for x. So plug it in the way you need to. So here is the absorbance. Here is my m. This is b. And I'm going to isolate and solve for x. What's the concentration? I can solve for the concentration by doing the, the math once I have it all plugged in. And here is my concentration. So you can use a graph to determine other, get other values for another problem. All right, so using the graph to calculate the molar absorptivity. How did I know that the molar absorptivity? Well, one, it matches up in here. But two, you can actually solve it with this problem if you wanted to. So you do m equals epsilon b, and then you isolate the epsilon. And when you do that, you have m over b. And it gives you the value here, and b is this path. Yes, I know it says b here, but the path length that we use in our experiments is 1.00 centimeters, and that gives you the molar absorptivity centimeters. Units. Sorry, I'm looking at the thing. So when you look at this, just know that m is this, okay? What is molar absorptivity? Well, I think I told you before. If you have two solutions that are prepared the same way, same concentration, same everything, but one seems far more intense than the other, that has to do with the absorptivity value. It has a greater value, which means it's going to absorb more than another solution that has a lower value of absorptivity, molar absorptivity. All right, so here's another problem. I'm giving you a few problems because this can be kind of confusing, and I want to give you guys enough information to hopefully get you through this. Use the graph to determine the concentration of an unknown dye with a 100 centimeter cuvette. So you have your absorbance is 0.25 at 542 nanometers. Pull out what you can from what you can determine. A is absorbance, C you don't know the concentration, B you know the path, and E you can determine the molar absorptivity from the graph. Plot it all out. Again, I didn't use, I don't know if this is a problem on LabFlow or not. This is from my prior semester. And again, I didn't use scientific notation, and there was a unit there. So the spectrophotometer, if we were in class, I guarantee you guys we would use this, and this is really not a difficult class. The graphing would probably spend more time than the lab itself. Turn on the instrument and the light source. Both need to be turned on. It will take about 20 minutes to warm up that light bulb. It's a special light bulb. It's not just what we use here. Prepare the samples in the blank. You always have a blank first that goes in and calibrates the spectrophotometer. That's how you calibrate it out so you can use your samples. Set a correct wavelength and measure the blank after the light source has warmed up. And then you measure the samples, and these give you values. Once finished, remove the samples, turn off the light source and the instrument. This is very simplistic. You need to watch the video, but this is a very simplistic instructions on how to do this. And this is what one looks like. They all look different. You see this one's different than this one. They all look very different, but they all do the same thing. Now we're going to get to the lab portion. So not only are you going to graph, you're going to have to do some things before you can graph. You have to get some values, and you're going to do some experiments. LabFlow is going to take you to another website, and this is a free website. There's actually really cool labs on here. They're all free to do, and they give you a visual of certain things. So I suggest that if you can access some of the other labs on this website, they're really cool. I'm going to break down what this is, but honestly, you should spend time messing with this before you start the lab so you know exactly what you're doing. So here is your drink mix. This is what you're given. This is the water. Your drink mix, you're going to shake this. See this little weird magnifying glass? This doesn't move, but this does. You're going to move that here, anywhere in the water. It doesn't matter. And the value is going to show up. Then you're going to shake this, and LabFlow is going to tell you how much it wants as a concentration. And then after you do that, you add water, and you can get it up to 1 liter. Then you can remove water by either evaporating it, or I never pushed this one. I did evaporation. But I think you can pull this too, and this will take water out. And you can slide the lever, to evaporate. And then you can change this to different other compounds and do the same thing over and over, and then the reset button. Once you're done with that portion, you're going to have a second half. This looks busy, but that's because of all my words. It really is not this busy. First, you're going to push the light source on. When you push the light source on, it's going to come across. It's going to touch this. Do not mess with this. Don't move this at all, because this is where the light source is the detector, and you're going to have information up here. Okay, so make sure you have the correct conditions, either present or variable. Make sure it specifies which one. And the wavelength will just be there. You don't have to worry about that. The cuvette, this is a cuvette. It can move out and in. And you can move this ruler, and you'll be asked to measure it. So you can move this and measure what the cuvette is. Also, you can change your molarity by here, and it'll tell you what it is here. And then you can pick transmittance or absorbance, and then circle to reset. And you're going to go again, drink mix, and there's a whole bunch of solutions, and you're going to go through different ones here. And you're also going to have to go through preset and variable. All right, so then there's some questions on lab flow, and I'm going to help you answer them. Vanadium, an aspect that can affect the color of a solution is the charge of the cation. So cations can change color of solutions. This one's a pretty interesting one. Lab flow is not actually asking about the different charges on an element, but more about the cation. But this one's cool because this is still the same element, but based on the different oxidation states, it gives different colors. Copper does the same thing. There's a few that do. And so, but this is like really opposite of each other, which is really, I like it. So cations can change the color of solutions. So can anions. I found this color on Reddit. It's pretty pretty. I like it. This is potassium dichromate versus potassium permanganate. So you see potassium is a cation, same cation, but different anions, and it gives you a different solution color. So you can see one is more orange or yellow in this picture, and the other one is purple. And you can see over here, this is potassium dichromate and potassium chromate, and you can see the color difference with these two. All right, so here's a sample graph. I think this is from LabFlow as well. And the only thing that's missing here is R square. You should have R square. Where does R square come in? Well, I'm going to explain that to you. When you have your data values, and you will know which ones they are, LabFlow will walk you through everything. You're going to graph. I used Excel, but I tend to use Google. What is it? Google Docs? No, Google Sheets. I tend to use Google stuff. But what I found is that when I try to use this stuff on PowerPoint and stuff, it doesn't come out well. Or at least I don't know what I'm doing. So what does this have? So I have my values so you can see them. And I have labeled everything that you should have on a graph. I have my equation. I have my R square. I'll explain that what it is right now. I have my units for X and my title. I have my numerical values and the same increments on this side, and absorbance. So what do you need? You need a best line fit. So you should have a best line fit. There's a little box that should be checked off for that. And it points to, ideally you want your data points to be as close to the line as possible, but does not have to touch the line. So this is the weird thing, is that the best line fit doesn't have to touch the line. You can have dots on this side and dots on this side. But it's more of I don't know how to explain it. It's more in the middle somewhere. Your video should talk about best line fit. That's how I've always known it anyways when I've graphed. LabFlow is a little weird on some of their things. Notice I have my units, best fit line, equation, R square value, my title, x-axis, y-axis values are included with units applicable. So when you look at this, this has everything I need to understand what I'm looking at. I have concentration and absorbance, standard curve for a drink mix. I have my data plot, my R square. R square is a number that is how close your data points are to the line. And the further your data points are out, the R square goes down. And the highest value is 1. So this is my example. Don't worry if you don't get one that looks like this. I want you guys to make the best effort you can. Put it together the way it should look. But if it doesn't look like this, you know, you do what you use different values, and it took you to where it did. That's it. Okay, so pay close attention to the videos and take notes. There's a lot in here. Pay attention to the videos and the notes. Pay close attention to worked out calculations. Some calculations provide wavelength. The wavelength in here just tells you what the experiment was done at. You're not using the wavelength in any of these. It's extra information, but you should have it. You will use Beer's Law, the equation, to solve for equations. Get comfortable with the PHET simulation. Definitely. Make sure you definitely know how to use that before you start. Follow instructions for the lab carefully. Write everything down. This is a long lab. If possible, print out the PDF. The PDF actually gives you the data report sheet, and it's pretty similar to what you're doing in the lab portion. So honestly, it would be, you don't have to, but if you're able to print out at least that portion, it makes your life a little easier. Give yourself enough time to complete. This is a long lab. This is not a short lab. That's why I disagree with it being with a second lab in the week. I like this lab, but I think it should be by itself. I did not use scientific notations or units in my answers, but Here's a problem that I'm giving you the answer to because I don't like how they asked it. You'll be asked about the intensity of a colored solution. But the problem is they don't really explain intensity. Nowhere could I find intensity. And since you're using kind of a program, it's not realistic to if you can see through it or not. It just doesn't make sense to me. So if I couldn't understand it, I don't see how you guys would. So your options are completely opaque, between opaque and transparent, or completely transparent. And I'm trying to understand, is transparent mean clear? Like they don't really explain it. So basically your answers are, for highlighted for tables 2 and 3 are the same answer, between opaque and transparent. But as for tables 2 and 3. Okay, and if you see this, I think you'll understand what I'm saying once you look at it. And that's it. Thank you.